Thanks, Joran, and thanks, George, for being with us. It's really my pleasure and privilege to introduce George Philander. George is one of the most preeminent oceanographers. He was born and raised in South Africa and received an undergraduate degree in applied math from the University of Cape Town to escape apartheid. He and his family emigrated to the US soon thereafter. He subsequently went to Harvard, got his PhD there, working in fluid dynamics and oceanography, and received a PhD in 1970. And during his early career, George worked on tropical ocean dynamics. So he was principally responsible for elucidating how the Pacific undercurrent comes about, a strong ocean current under the equator that seems to go the wrong way around. He elucidated how waves in tropical oceans are excited and respond to changes in wind forcing. So that was all in the 1970s, late 1970s, early 1980s. And then 1983, there was a strong El Nino. So after that El Nino, George helped lead a decade-long observational program in the tropical Pacific called TOGA, whose results ultimately cemented our current understanding of ENSO. So what you now learn in our classes, how ENSO works, that goes back to TOGA, it goes back to the wave dynamics that George elucidated early in his career. George himself wrote the textbook on El Nino, which I'm sure many have seen. And sometime in the course of that work in the 70s and 80s, and not quite sure when, George coined the term La Nina. So we all talk about La Nina now, but that was his word. Has entered our lexicon. So George helped us make sense of what is going on in the Pacific now, La Nina conditions. He helped us understand that La Nina is part of a nonlinear oscillation and the ramifications it has on climate globally, and he gave us the language to talk about it. We should all be thankful for that. And beyond that, I'm personally extremely thankful to George for his wisdom and mentorship over the years, which have been really essential for my career. When I was a grad student, don't know how it is for you grad students now, but I was looking around me to see whose life seemed worth emulating. And I think George was the scientist I admired most of all the scientists I knew. Not only is George an outstanding scientist, an outstanding oceanographer, his broad interests across and beyond the sciences are just amazing. He's a gifted musician, many evenings of playing music at his house. And you can talk with him just about anything, from advantages of vinyl for music recordings to could see his literature and understanding of South Africa. And what I don't think many people know, George is probably more responsible than anyone outside Caltech for the fact that I'm at Caltech. I don't know if George knows this. When I was agonizing over what to do after graduating in Vertigo, I went to talk with George. I went to talk with many people, but the conversation with George was most memorable. What he said was simple and wise. He just listened, and at the end he said, well, it sounds like you like Caltech. Why don't you just go there? It's not a life or death decision. If you don't like it, you can just change your mind. And that was just pure George, simple, straightforward, and wise, and I've always appreciated it, and I'm happy he'll be speaking to us today. So without much further ado, I leave the screen to George, and he'll talk about whether global warming is inhibiting an incipient ice age.
Okay. Well, thanks for those kind words, Tapio. I hope at the end of the seminar you will still be inclined to say kind words. It will turn out the two of us actually disagree on some scientific issues will come out. Just as a quick aside, the problem I talk about, global warming, has two facets that overlap. The one is scientific, and the other one is ethical. And I'm hoping tomorrow to get a chance to speak, especially to the students. I don't at all agree with the current policy we're following, how to cope with global warming. It has to do with the ethics of it. But for the next hour, I hope I still have an hour. We had a very lengthy introduction there. We'll just confine attention to science. So let me start with an easy question. Suppose that the only information we had about Earth's history, the climate variability, is the top figure. And it goes back to, it tells an amazing story. It goes back to, that figure goes back to the time of the dinosaurs disappearing. And you see Earth cooling off. Then something strange happens around 3 million years ago. and these amplifications that amplify dramatically take over. And at the end, we're at this precarious moment. We're at the interglacial, and these big ups and downs you see on the screen are the current ice ages. And if this were the only information we had about Earth's climate variability, and I ask you what's going to happen next, you can confidently predict that an ice age is imminent. And then if I were to ask you to, how soon will that be? You will look at the time scale, it's millions of years. You'll say, oh, any millennium now. And so there is nothing to worry about, the imminent ice age. However, if we go to the bottom picture, I provide additional information. And although it looks simply as a blow up of the top picture for the last 100,000 years, it's actually an entirely different data. The top is by drilling into the seafloor and looking at oxygen 16-18 ratios. The bottom is drilling into the ice over Antarctica and looking at entirely different variables, which then gets translated into temperature and carbon dioxide. And you find that we have quite a bit of information about the carbon dioxide fluctuations that accompanied this ice age, the current ice ages. And then the spike you see at the very end, that's us human activities. So we appeared very recently, and we advanced with impressive rapidity. And then an inadvertent byproduct of our activities is the spike in CO2. That is now causing alarm among some people and denial on the part of some others. So now if I ask you what is going to happen, I'm particularly interested in the next few decades. You could look at this and say it should be possible to use this data we see here. It doesn't look very complicated. It's certainly not chaotic. And given all this information, it should be possible to extrapolate and make a decision about what is going to happen over the next few decades. And that would be a strictly empirical approach. I won't invoke any model. I'll just look for correlations and so forth, and make this prediction that it looks as if global warming, there are going to be changes. Now, unfortunately, we can't do better than that. And there are huge error bars on whatever prediction you make. And the reason, in the words, this is, I'll show the next picture. No. Okay. I'll call that a holistic approach. It's really empirical approach. And you see the opinion of Hodel. We really cannot extrapolate because we don't understand why there were ice ages. And his opinion is shared. There was a committee of 20 odd people who met over the course of several years, several times. They wrote a long review paper and came to this same conclusion, that we don't have an explanation for the ice ages and cannot easily extrapolate and anticipate what's going to happen over the next few decades. So then we can take an alternative approach. We could say, forget about this past data. We treat it as an initial value problem. We know the laws that govern atmospheric motion, oceanic motion, that govern climate. We've built models, lots of models around. And the top sentence is actually a statement by two prominent modelers. One is Tim Palmer, a professor at Oxford. The other one's Bjorn Stevens. You may know him. He used to be at UCLA. He's now director of the Max Planck Institute. And he said there's this deep dissatisfaction with our model. And you can read that for yourselves. So we're a bit of a bind. We have these two possible approaches, and neither of them seem to work. And what I'm trying to persuade you today is that we should marry these two approaches, the holistic and the reductionist. And the people who, the entirely different approaches, the two prominent figures in the holistic approach would be Charles Darwin, the fellow who discovered that the continents drift. And on the right-hand side, you have the two big reductionists, Isaac Newton and Einstein. And the I think Darwin, when he published his book, sometime in the 19th century, was asked whether his theory for evolution was consistent with Newton's laws. And he said they're entirely consistent, but they don't really do you much good. If you want to explain how humans came to be here, it doesn't do you any good to write down some equations and solve them and say, therefore, man is here, Homo sapiens are here. Instead, you tell a story, and then you could start with the dinosaurs and so forth. So two entirely different approaches. And so one challenge in trying to marry these two approaches is it's actually very difficult. I'm in the department at the university where we have world-class paleontologists and we have world-class climate dynamicists. And I should probably whisper this, but I assure you interaction between them is really minimal. They speak different languages. And it's not, so for the last few years, I've gone around and at the bottom I've listed some of the people from whom I've learned quite a lot. But my main message to you is that this marriage is not, it's not being productive yet, and that's the challenge. We could learn from atmospheric scientists, from meteorologists in particular, who have succeeded in marrying these two approaches. And on the one hand, they, up to World War II, where the prediction was strictly holistic exercise. They knew there were highs and lows and they could produce maps. They didn't know why there were highs or lows or warm fronts or cold front. But meteorologists could produce these weather maps because they had the telegraph. And on that basis, they could make predictions. After World War II, or during World War II, a computer gets invented and people developed models. And it was an exciting period in meteorology. The computers were poor, and so they had to simplify the equations. We had quasi-geostrophic theory and so forth. But it took something like 30 years before these two approaches were married successfully. And today, weather prediction is our most spectacular success. And what's particularly fascinating is that the models have been tuned on the basis of measurements so as to produce the right correct weather forecast. But at the same time, the models are so good that if some measurement is errant, if there's something wrong with the instrument, the models can actually identify where this instrument is and where it should be replaced. So it's a beautiful marriage of these two approaches. And the snag with it, it only works for about 10, 20 days. That's sort of the limit of weather forecast. Can we do better? And we can. I mean, I cannot tell you what's going to happen in Pasadena more than 10 days hence if I use weather forecasting models. But I can confidently predict that it's going to get much colder over the next few months. And if you wait 6 months or so, it's going to be much warmer. In other words, the climatological seasonal cycle is extremely valuable tool. So at the moment, on the strictly empirical basis, you can make a forecast 6 months hence. The forecast will be the same for all Junes in future, or Julys and so on. And it cannot distinguish between, every June is distinct or every January is distinct. It cannot do that. And so the challenge for us modelers is, can we produce, can we improve on that feat? And I'm going to argue yes, and I'm going to say what I hope to do is persuade you that a combination of these two approaches, we can use the paleo data to tune the models. And we have to focus on the seasonal cycle. As I said, the seasonal cycle is a very reliable signal. However, we see only one of several possible seasonal cycles. So the seasonal cycle is the tilt of the axis, the eccentricity of the orbit, the precession of the equinoxes. And so okay. Uh, I assume everybody can hear that voice. Anyway, now I lost my thread. Okay, so if I go to a seminar, which is obviously often, then I consider it a success if 2 weeks later I can remember one important thing that the speaker said. So here is the important thing I would like you to remember 2 weeks from now. And I'm going to ask the problem we're having with the paleo data and interpreting the records. I'm going to say that we should ask ourselves, are we asking the right question? And I'm going to argue that we've actually been asking the wrong question. The question we've been addressing, why do glaciers wax and wane, has proven profitable for more than 100 years. And it started out with people seeing this, it's called an errant boulder, the big rock at the bottom of the screen, bottom right. And you could ask, how on earth did this rock get here? And if you're wandering around Switzerland, you see rocks like this, you look around and you say, it must be the glaciers over there. Whatever giant brought this rock here has disappeared, and glaciers are entirely capable of coming and going. And Milankovitch had the bright idea that the changes in sunlight and its orbital parameters are responsible for glaciers waxing and waning. And that's proved a very profitable question to pursue for the last 100 years. But I think it's run its course. We have to ask new questions. And the main problem with this question, why the glaciers wax and wane, is it implicitly assumes that the ocean will obligingly provide fresh water for glaciers and then fade back into the background, and that the atmosphere will obligingly transport that water from low to high latitudes. And I submit that neither the ocean and atmosphere are quite as cooperative as that the story, this drama of amplifying ice ages in the last 3 million years had 3 protagonists: the atmosphere, the ocean, and the glaciers. And as far as now we have to go back again. Milankovitch was handicapped by not having a computer, and he wanted to calculate how sunlight changes. So he chose 60 North on June 21 at the solstice. He said that's what can affect glaciers the most, and he made the calculation. And to this day, you get many, many papers in paleoclimate will show sunlight at 60 North in June. And I'm going to try and persuade you that it's a complete red herring, that it's the most misleading thing to look at if you're going to explain ice ages. And so the thing about taking the atmosphere and ocean into account is that they couldn't care less about sunlight at 60 North in June. What they care about are sunlight gradients. So the atmosphere is really driven by the pole equator temperature gradient or sunlight gradient, and the response of the atmosphere to that is what drives the ocean. So once you turn your attention to global Milankovitch forcing, you have new questions, and I'm going to pose 3, which I will try to answer in this talk. The intriguing Milankovitch forcing, the changes in sunlight because of orbital parameters, has 2 main components. The one is precession, and I'm going to assume, I'm talking to people at Caltech, I'm going to assume people know what precession and obliquity mean. And the intriguing thing about precession is that it redistributes sunlight over the course of a year. So the Earth is moving very fast when it's close to the sun. It's called perihelion, and it's moving very slowly when it's far from the sun. And if you integrate the change in sunlight over the course of a year, the answer is 0. Precession is redistributed. But I'm going to show you records in which there nonetheless are signals with a 20 kiloyear cycle. And you're going to immediately conclude that precession must be a nonlinear phenomenon. If it were just linear, then 0 change in sunlight over the course of a year is not going to produce much. Obliquity poses a similar question, except that obliquity, if you take a sphere and all you do is change the tilt of its axis of rotation, you would not have changed the net amount of sunlight on the sphere. All you would have done is redistributed it. And nonetheless, global average temperatures change with a 40 kiloyear period. So it's very important to remember these numbers: 20,000 years approximately for precession. There's actually a few more periods involved. 40 for obliquity. And then the third one is very intriguing. It's called a sawtooth. And it refers to these recurrent signals you see over the last million years or so. And you notice that glaciation is a very gradual process, and then deglaciation is more rapid. And that's why you get the sawtooth. But the thing about the trends of this type is if you want to explain them, you have to look for feedbacks, and then you have to look for thresholds. And I'm going to submit that the Earth would have had the recurrent ice ages, even in the absence of Milankovitch forcing. Because what we have to look for is nothing really to do with the forcing. It has to do with feedbacks and with thresholds. And I'm furthermore going to propose that preceding, so the sawtooth signal is only there for the last million years or so. Preceding that, there was a very prolonged cooling event. And it started about 3 million years ago, continued unto 1 million years ago. And now you can see why originally, when this type of time series first became available, people Fourier analyzed it. That was after World War II. The Fourier analysis came up with the peaks at 20, 40, 100 kiloyears. And those are exactly the ones you get in the Milankovitch forcing, the orbital parameters. And so people were quite euphoric about this and thought this is the answer, that the Milankovitch forcing is what drives the ice age cycles. And I'm going to say in the absence of Milankovitch forcing, you would still have ice age cycles. And what the Milankovitch forcing does is add some periodicity. The cycles would be quite irregular if it weren't for the Milankovitch forcing. But apart from that, it's not particularly important. We'll come back to this later on. So try to remember questions A, B, and C. I'm going to start with C. And question C asks whether the sawtooth and its preceding trend could be natural climate phenomena. In other words, they don't depend on forcing. Right? So we have lots of examples of natural phenomena. Weather is one, El Nino is another one. You don't need to force them. They'd be present even if there were no variations in sunlight. So let's proceed. Okay, so the slightly unusual thing I'm going to do is, people usually tell you if you want to understand the present, you should look at the past. And I'm going to propose that to understand the past, you should look at the present. So a backward approach. So this is the climate of today, and it's the climate on the basis of data. We don't have much data in the last 20, 30 years. There's lots of satellite. I'm actually going to show you slightly, it's the same picture. I prefer the color scheme here. This data is not as accurate. In fact, I don't think the data from the top picture overlap with the bottom, whereas in the previous picture they do. But let's look at this one. And I'm going to argue we live in the most astonishing world, at the most peculiar climate. You see these strange asymmetries. If you look at precipitation, you see the ITCZ where precipitation is heavy. That would be the yellow-red colors. And it's decidedly north of the equator. So this is average over some two decades, I think. And it eliminates the seasonal cycle, it eliminates the diurnal cycle, it even eliminates El Nino. So this is average, a long-term average. And so you have this north-south asymmetry. You also have east-west asymmetry. Why is the eastern, along the equator especially, why is the east colder than the west? And one intriguing thing about this climate is the high correlation between an oceanographic variable, sea surface temperature, and atmospheric variable, precipitation. And it's been demonstrated that given the top picture, if you give meteorologists the sea surface temperature, they can explain the bottom picture. And it's fairly easy that the air will rise where the sea surface is particularly, the temperature is particularly high. It rises into tall cumulus towers. They produce the heavy rainfall you then see over the warm water. What goes up must come down, and much of that air subsides over the adjacent pools of cold water. And so in the bottom picture, there's the white, those are these regions. And even though there's no rainfall here, this is very cloudy. You get low-level stratus clouds cover these regions. And if you were to fly from Los Angeles to Hawaii over there, you look through your window, you'll see this bank of clouds below you, low-level stratus clouds. And as I said, not only given this, the top sea surface temperature, you can then produce this, explain this. If you were to run a model in which you allow this to vary on a long time scale, for example, include things such as the seasonal cycle and El Nino, you can reproduce the seasonal cycle and El Nino in this picture. Okay. So all the information, or much of the information you need to reproduce this atmospheric state is due to the ocean. And it turns out that the converse is also true. If I'm an oceanographer and you ask me, explain this, then I'll say, you have to give me this information about the atmosphere. And the key thing in this picture is that the sea surface temperature pattern reflects variations in thermocline depth. So now I have to explain to you, I'm going to assume, I'll spend a few minutes on the ocean. And here I have to go to the next picture. So I'm going to explain how this comes about. It starts with measurements of the ocean thermal structure. And the big difference between the atmosphere and the ocean is that the atmosphere is heated from below, it's very turbulent, it adjusts very quickly. This is what you do when you boil water for your coffee in the morning. You have an alternative strategy. If you want to read War and Peace while you wait for your water to boil, you can heat it from above, but this will take forever. And so we usually adopt that. And so we've had forever for the ocean to warm up. So it's a puzzle, why is the ocean so cold? And I would argue probably the most interesting in oceanography is precisely that. Why is the ocean so cold? If I go to the warmest place at the surface, say the dateline at the equator, and I take the average temperature for water column, it's barely above freezing point. The ocean has had forever, had billions of years to warm up. And so the big conclusion I can draw from this picture is that the ocean must be in motion. And the challenge now is how does it move? And the properties of the deep ocean below the thermal. So the thermocline is what separates this water. I've lost my scale. This water is about, I think, 28 degrees centigrade, but higher. This is about 3 degrees centigrade, 3-4 degrees. It can be below 4 because of salinity. And it's so remarkably uniform that we conclude the origin of all this deep water must be a few very high latitudes. And those high latitudes at the surface determine the properties of the deep ocean. So on this basis, people came up with this famous picture. And I'm impressed with what our geochemistry friends accomplished. This picture is on the basis of chemical measurements, because it takes about 1,000 years for the water it sinks in the North Atlantic, and to get over here, it takes about 1,000 years. You can't build a current meter that will measure such slow speed, so it's inferred from chemistry. And the slight problem with this picture, it's wrong. It figures in various movies and so forth. If you go to downtown Pasadena, I'm sure, ask a random person, they will know what the thermohaline circulation is. I'm impressed with what the geochemists accomplished there. As I said, the picture's wrong because the water does not rise here. We don't know where the water rises, or we didn't know for a long time. And the problem was that in this equation that governs the temperature of the ocean, if this picture assumes that these two terms are in balance, that water is rising everywhere, and the rising of cold water is balanced by downward diffusion of heat. And then if you measure the kappa, the diffusion, it's too small by order of magnitude for this balance to be valid. So we have to modify that this has elements of truth. Water is sinking North Atlantic. It does fill up most of the deep ocean. But the rising part is all around Antarctica. It's not elsewhere. So independent of this thermohaline circulation, the people, Stommel and Woodsell in particular, studied the wind-driven ocean circulation, and we get these gyres. And then, much more recently, a decade or two ago, they added the third dimension. So it wasn't just a horizontal gyre. The wind-driven circulation has a vertical component. And this shows you the trajectory of a few water parcels. They start at the surface, and then they drift this way. And yeah, where the dots are once a month where a water parcel is. So here they're moving very rapidly. They're quite far apart. This is the Kuroshio current. Some move to the equator. There's the equatorial undercurrent, the type you mentioned, and it starts deep, comes to the surface. And to complete this trajectory takes about several decades. These in particular are the trajectories over 30 years, as I said, in a very realistic ocean model, forced with realistic winds. We can draw similar pictures for the Atlantic and so forth. There you have the Gulf Stream and so forth. So the picture that now emerges for the ocean circulation is, it has two components. It has a thermohaline, and then it also has this very shallow, we call it ventilated thermocline. And jointly, the two constitute the global oceanic circulation. Now, on a long time scale, and this is a particularly important picture, what this circulation does, these two components jointly, is maintain a balanced heat budget for the ocean. But it's going to be maintained on the time scale of the ocean circulation. It cannot be accomplished shorter. And that time scale is decades for the wind-driven part and centuries for the deep part. So let's just assume for the argument, we have the ocean, it's this body of fluid. It has a well-defined top, bottom. Let's assume that the bottom and the sides are insulated. The only heat flux at the top. Then on this long time scale, there must be a balance between the heat gained and the heat lost. Okay, but you can only expect that on time scales of decades, centuries. Now, suppose we do an experiment, and we've done this in an idealized model. Suppose we shut off this loss of heat. The loss of heat is mainly in winter, where very cold continental air blows over the warm Gulf Stream, Kuroshio here, same over the Gulf Stream there. So you get these dense fog banks over these parts of the world. As I said, cold air. Now, suppose we do an experiment and we suppress the loss of heat here. Then at first, global warming is in fact doing that. At first, the tropics won't know. And so warm water keeps on pouring into the ocean. I'm sorry, heat keeps on pouring into the ocean. And as a consequence, the thermocline deepens. And it's a very important result. It tells you that you can control the depth of the tropical thermocline from high latitudes, right? If you, as I said, if you change the loss of heat here by changing atmospheric temperature, in due course, there must again be a balance. You have to reduce the loss of, you have to reduce the gain of heat, and you accomplish that by pushing the thermocline down. So the main point of this picture is to tell you that ocean and atmosphere interactions can lead to a broad spectrum of climate variability. And in particular, low frequencies, we have little data, but we all know about El Nino, La Nina. So this picture, that line is the thermocline, and during El Nino, this thermocline goes up there, goes down the other side. So El Nino is really an adiabatic interannual oscillation. And it involves feedbacks. For example, the equatorial winds during El Nino collapse altogether. They're very strong here. So this has been studied to death. This part is unexplored. So it's also possible to have this diabatic change. And Cristina Ravello introduced the names El Padre and La Madre. And so confusion in terminology. El Padre, if this thermocline goes down deep enough, you won't have any El Nino at all. And so at some point I call that the permanent El Nino. It's sort of misleading. It's permanent El Nino is this diabatic process. It's just the El Nino. There's even debates in the literature about this, but the debates stem from poor nomenclature. So I want to focus, we know little about this for the simple reason that the timescale is very long. This requires that the whole ocean circulation come into play, that there be a balance between heat lost and heat gained. So it involves all of this. And I'm going to argue that this is actually, this mode, climate mode, is a central part of the recurrent ice age cycle. So I'm going to argue El Padre La Madre. What you have, it's a multi-decadal diabatic basin mode. It's actually global. And what you have is, if you go to this picture here, think of these stratus cloud covered regions where it doesn't rain. Think of those as the tropical counterparts of glaciers, right? So simply albedo is very high. So in tandem, suppose a glacier grows, it waxes. In part it waxes because of this albedo feedback. The bigger a glacier, the more sunlight it reflects, the lower temperatures, the more snow you'll have. During that time, the ocean loses more and more heat, and so the thermocline actually rises. The thermocline goes up at the equator because you have to increase the absorption of heat. So the upwelling zones expand. So all of these. So it's for music to think this is the climate of today, and it looks quite cold. During ice age, this areas probably expanded enormously. The warm regions contracted. And then during a warm period, it's the opposite. So think of this, and here I've mentioned some of the stratus cloud feedbacks. So on the basis of this result, and we have support for this from very idealized models, I can now go on and answer question C, as stated earlier. The question C said that could the trends be a natural mode of climate fluctuation, quite independent of Milankovitch? And I would say, yes, indeed, they could. And the feedbacks that keep them going are the cumulus cloud. Lots of feedback. Cumulus clouds over warm water. As the moist air rises, it releases latent heat and so on. That's what keeps hurricanes going. There are stratus cloud over cold water. You create a temperature inversion. And if you, the clouds themselves will increase that in temperature inversion. If you lower or raise the thermocline. Anyway, it's sort of obvious what's going on here. Atmospheric dust is another one. As the temperatures go down, the atmosphere can have more and more dust. But there are also thresholds for these things. From a combination of these and these, I can go back and provide explanations for many of these features I've been talking about. So you can ask, how do I test these? These are all conjectures. These are also very idealized models. There's a whole set of, this is the first test. I can rise and lower the thermocline by changing the water that sinks in at depth at high latitudes. So from 60 million years when the dinosaurs appeared to 3 million years, there's been global cooling, mostly because of lower CO2 continents drifting and so on. And that global cooling caused the water sinking into the deep ocean to be colder. So 60 million years ago, the deep ocean was about 10 degrees centigrade warmer than it is today. Okay, so I would submit that that cooling resulted in an elevation of the thermocline. And the elevation around 3 million years ago gave rise to the appearance of cold water at the surface. And again, these are trends. So in the warm pool in the Western Pacific, sea surface temperature hasn't changed much over the last 3 million years. Whereas the water in high latitudes and the water in the tropics, and even this is the east-west gradient, this is the north-south gradient, they've experienced, anyway, this is basically confirmation for what I've said here, that we have this mode. We actually is such a thing, right? We have to rely on the paleo data. We don't have enough data to check this, but at least the paleo data I can interpret in terms of what I see. I can explain this to be consistent with that mode I just mentioned. Now, an additional check comes from bringing in obliquity. And so this is interesting. I'm going to argue that the trends and feedbacks give us a very broad spectrum of climate variability, and that the broad spectrum is a consequence of the atmosphere, the ocean, and the glaciers having entirely different timescales. So you have three systems. Atmosphere, if you give it a kick, if you some quick adjustment, it comes back into equilibrium within a week or a few weeks. The ocean's much slower. We just said it takes, if you change the winds, it takes forever, decades to centuries. And glaciers are so slow. I mean, in the English language, if you're moving at a glacial speed, it's forever. So these three elements, the protagonists in these interactions, have such a wide range of timescales that they give a very broad spectrum of climate variability. And so we have everything from daily changes in weather to interannual changes in El Nino to these decadal and centennial oscillations. And I'm going to argue that if you now go back, obliquity, and later we'll talk about precession later, those can be regarded as experiments nature does for us. So you have a very broad spectrum of climate variability. Superimposed are very narrow spectral peaks. And it's a little bit, if you study tides in the ocean, tides are changes in sea level. And what's fascinating, sea level fluctuates of a very broad spectrum. The tides are very narrow peaks. And what's intriguing is the narrow peaks are really tests for theories about variability of sea level in general. And for example, if I turn on the winds over the ocean, suddenly I can have an elaborate theory about the waves that propagate back and forth. They go eastward along the equator, they go poleward along the coast of California, then down along. And I can describe these in terms of a read function. So how do I know that the properties of those waves have anything to do with reality, what I get from my theory? And the tides provide this spectacular example. So the ocean gets forced and very precise periods, 12.6 hours, 1 day, 14 days, and so on. And the structure of those tides tell me that my theories concerning equatorial waves and so forth are correct. So I'm going to argue similarly that obliquity and precession are very narrow spectral peaks, and those are actually beautiful experiments that nature performs, and we can test our theories. And for example, the amplifying, let's start with obliquity. So all you do is change the tilt of this axis very slightly. You're not changing the annual average sunlight at all. And these observations, obliquity turns out to be the pacemaker for the sawtooth in 33 out of 36 cases. It's quite astonishing. Furthermore, the sawtooth period, if you analyze the data carefully, Peter Hoybers, Carl Wunsch did this, the sawtooth period recurs either every 80 or 120. You get this from a histogram. So to say that the sawtooth period is 100 kilograms is actually simply an average of 1820. And all of, I suppose the main point here is that the sawtooth signal and the obliquity signal is basically the same mode. The one is natural and it comes in trends with thresholds and so on. The other one is oscillatory. And Peter Hoybers pointed out this amazing thing, 336 cases of degradation of the past 2 million years were paced by obliquity. And the question, you ask, why can obliquity be such an effective pacemaker for sawtooth? It basically is the same climate mode. All of this calls for a new taxonomy for ice ages. So when I go to seminars of paleoclimate, always impressed, the audience can refer to MIS 11 or 3, and they'll know exactly what they're talking about. And the rest of us, so in other words, they've created this taxonomy, and presumably the gray, to me, I must confess, looks rather arbitrary. The gray is supposed to be periods of glaciation, and these are interglacials, I think. Anyway, I propose a different taxonomy. Let's choose these abrupt changes. So this is deglaciation, and this is glaciation. Let's choose this instead. And now, I mean, the whole point of a taxonomy is you want to know what all glacial maxima have in common, and why each one is nonetheless distinct. And similarly for deglaciation and so forth. So I would submit that this one makes more sense than this one. I hope I'm not offending on. Interesting thing emerges. I previously mentioned 33 out of 36 cases, according to Peter Hoybers' tabulations. Obliquity was increasing whenever there was deglaciation. This is one of the 3 cases that doesn't conform to that. Here, obliquity was doing the wrong thing. So we have to look carefully. It turns out if you go further back, there were 2 more such peculiar cases. And so these exceptions are worth exploring. And this then brings me to the precession signal. So I'll claim that I've answered the question concerning obliquity. The reason I asked previously, how can obliquity, by merely redistributing sunlight, cause a drop in global temperatures? And it's not only because glaciers grow and decay that changes Earth's albedo and changes temperature. It's also in parallel with the glaciers growing, the tropical cold water expands and its stratus cloud cover increases. So as I said, we can look at this picture in detail, but I'm running out of time. So let me turn to precession next. And precession poses many problems. And if you want some guidance on how to pursue this, you must read a little bit. Conan Doyle wrote this book about a horse. That's the name of a horse. And they had this conversation. And precession poses very similar questions. So this is the precession signal in various regions. This is a monsoon one in the Chinese caves somewhere. This is sea surface temperature, the Eastern Pacific. This is glacier record. And over here, the dog is barking all the time. And as I said before, this one is easy to explain. The dog is very friendly. It seems to welcome people. And precession needs a nonlinear seasonal cycle. And the nonlinearity here is quite obvious. If you have rainfall, the monsoons are strictly rainfall in summer, it doesn't rain in winter. So if you intensify summer sunlight, you're going to get stronger summer rainfall. However, the counterpart will be when summer sunlight intensifies, winter sunlight weakens because the annual average doesn't change. So that's a nonlinearity, even though when the sunlight weakens in winter, since there is no rain, it's not going to decrease. Okay, so the nonlinearity here is obvious. And you see the precession, the sunlight is modulated by eccentricity. And the change in amplitude here is actually due to this change in intensive sunlight. So this has a very obvious explanation. If you then turn to the glaciers, Oh, I should point out that there are exceptions to this. There is a recent paper by someone in Arizona, Beck, and it does not look at this at all, even though it's a few hundred kilometers away. It is also in eastern China. And that record looks much more like this one. So Mr. Beck proposes that it's the glaciers. So what's happening to the glaciers is the dog doesn't bark all the time. So over here is a big precession forcing, and there's no response. Over there, there's a response and so on. So what's going, why is this so sporadic? And if you go to the Eastern Pacific sea surface temperature, you'll find it similarly sporadic. There are occasions, I call them Q, where there's no response, and there are other occasions where you get a big response. Why would that be the case? So to get a response, as I said, the forcing must be not, the seasonal cycle must be nonlinear. So what happened now? I seem to have lost the picture. Okay. Look at this picture. This is from moorings we have along, this is along near the Galapagos Islands, this picture. And it shows, it has lots of information. Let's just focus on sea surface temperature, the colors. The water there is very warm. And this is month. I seem to have done a poor job here. This is going from, this is March, and this is September. So this is going from January to the end of the year. And the arrows are the winds, and the contours, rainfall. But what I want you to draw your attention to is that sunlight crosses the equator twice a year. But there is an annual fluctuation in temperature along the equator. Sunlight here is, oops, sunlight there, sunlight here is the same as sunlight here, but here temperature is high, here is low. So it's a very nonlinear response. And if you want to know, this is the same information for a meridian further west. So this is the meridian where Hawaii is. And if you go, and what you notice is the picture becomes much more symmetrical, right? So here we get a highly nonlinear seasonal cycle. Here I get a much more linear. If I go way over to the date line, it becomes even more symmetrical. And I would argue the reason for this highly nonlinear has to do with the shallowness of the thermocline. That if you, there are earth interaction modes that give you linear, those are east-west. You also get north-south. If, suppose you had a symmetrical world, you put the ITCZ on the equator, then if you perturb it, move it north, the winds that converge under the ITCZ will cause upwelling at the equator and keep the ITCZ north. And this means that the ITCZ can be either north or south of the equator. However, the geometry comes into play. It's a long argument. And the short of it is that I can explain the north-south asymmetries as a consequence of earth interaction. But it only works when the thermocline is shallow. So if I were to go what I previously called a permanent El Nino or the El Padre phase, those asymmetries should disappear if this theory is correct. So I can now go back. Where was I? Okay, so I showed you these. And so I claim that what happened here, but I did some calculations with a colleague and a simple model. And it turns out that to get a highly nonlinear seasonal cycle at the equator, the thermocline, if it's too deep, you'll get a linear seasonal cycle because upwelling is much more difficult. On the other hand, if the thermocline is too shallow, you also get a linear seasonal cycle because the effects of upwelling dominate completely over the effects of sunlight. So tentatively, there are all sorts of puzzles now that can be clarified. And I would argue, Peter, there's a long debate about why is there a precession signal at all in the records of glaciers? Because they're so slow. They cannot respond to seasonal changes in sunlight. And even Milankovitch pointed this out in his original paper, that the precession, you should not expect a precession signal in glacial volumes. And Peter Hoybers has several papers, and he tries to, so glaciers won't respond to sunlight at 60 north in June. It will respond on some average because it's moving very fast when it's at perihelion. The moment you average sunlight, you filter out precession. So the presence of a precession signal in records of glaciers is a puzzle. And I will submit that what happens is the glaciers are responding not to local sunlight, they're responding to tropical equatorial sunlight. And it's really this signal that's forcing this one. So I think I'm aware of my time, so let me conclude. Precession, we can explain various things. We can Eastern Equatorial Pacific SST, the nonlinear. And because of that, I could explain why glaciers have why the monsoon is sometimes off. The main point here is that precession creates numerous tests for climate models. Because precession, if that response depends on the depth of the thermocline, I've earlier argued that thermocline moves up and down depending on obliquity and the sawtooth. In other words, the three prominent cyclic signals in the climate record, their superposition changes continually. And so if you're going to simulate something, you have splendid tests now. And the beauty of the seasonal cycle, it's so short, you don't need to run your model for 100,000 years. We don't have computer time with that to do that many times. I propose that we can, this is my proposal, that by exploring the seasonal cycle, we can have tests for our climate models and improve them. One thing I've not mentioned at all, I've spoken mostly about the Pacific, the Atlantic versus the Pacific. So the Atlantic is much smaller. And in the Pacific, the seasonal cycle, you cannot change the thermocline this way, the way El Nino does, because the time scale is too short. However, in the Atlantic, you can. And this brings me to my final comment. Today, this is what the Sahara looks like. And if you ask from an astronomical point of view, what's special about today, it turns out perihelion today is in early January. It's very close to the southern summer solstice. So the climate we see today is actually the climate of the cold phase of a precession signal. 10,000 years ago, the Sahara looked like this. Obviously, this picture was taken today. But if you look heavily at these rocks, there is lots of information. People have made drawings of animals. Anyway, it's a fact. You find fossils. It's a fact that the Sahara had lakes 10,000 years ago. The lakes, if you ask where that fresh water go, it flowed into the Mediterranean, and it gave rise to the striated outcrops. And so this is actually an island just off Sicily, and people have dated this. And so there is a precession signal. But my bottom line is, I hope I've introduced you to a new orchard that's quite unexplored. All I've done is review a lot of idealized studies, and I'm trying to argue that looked at from the right perspective, they actually explain the paleoclimate record and tell us that the paleoclimate record has a wealth of information that can be used to test models. The one thing, last thing I should comment, is the matter of abrupt climate changes, so-called. So I've said nothing about that. Many people are under the impression, or they claim, that these abrupt climate changes are extremely important to ice age cycles and so on. I'm not so sure at all. I should point out that a climatological seasonal cycle is a bit misleading in that if I give you poor data, say for the last 100 years, on that basis, you can calculate a climatological seasonal cycle. It would have filtered out daily changes in weather. filtered out things like hurricanes. However, we know that weather is extremely important in determining the climatological seasonal cycle, because weather transports heat from low to high latitudes. So it's quite possible that the so-called abrupt climate changes are fairly high frequency phenomena relative to the ice ages that nonetheless contribute to the ice ages. So that's a possibility. I haven't mentioned at all. At the moment, Majid Latif in Hamburg is simulating the last, it goes back 120,000 years. He's been simulating 120,000 years onward. There's a group at NCAR simulating, I think, from 20,000 years onward. And the value of those simulations are they explicitly resolve abrupt climate changes. So we should be able to find out, I can't think of any other way, determining whether those abrupt climate changes are actually important to the long-term averages. But as I said, I hope I've persuaded you that we're at a stage where exploring the seasonal cycle could be extremely valuable. And I have how we organize ourselves, and I hope to talk to Tapio and people at Caltech. I don't believe, there's a book called Little Science into Big Science by De Sola Price, and I highly recommend, you can download it free of charge from the web. It's worth reading. It was published quite a while in the 1960s. And some physicists commented that scientists are as interested in the history and philosophy of science as birds are in ornithology. So I hope that you'll be more interested in the history of science than birds are in ornithology. We really should, I think I'm not happy with the way we organize our activities at the moment. We've run into big science, and so we have a committee of literally hundreds of people called the IPCC. And I find that they dictate what should be done, what calculations. And I find it strange everybody obliges them and makes these calculations. And so they made a calculation, the last glacial maximum. So there are papers written, I know, a dozen different models all simulated this. I have to say this is not obvious to me what we've learned from this exercise. We really need a little science approach where people with rather slightly crazy ideas come to the fore and decide on an agenda. But we sort of abandoned science for the sake of curiosity. We're so keen on giving advice and doing models that tell us what's going to happen that we've forgotten, I feel we're neglecting. And so that's what, so I'll be available tomorrow if anybody wants to discuss. And this is, I feel, I'm an old man now, and but I've discovered that if you become old, you declare yourself a success and you want clones, you want people to do what you do. And it's only the young people who I think are actually willing to do something different. So anyway, I hope we can have a discussion, and I hope, especially looking forward to chatting to the young postdocs and students at Caltech, because I think a different approach to the one we're currently adopting is needed. I hope I've not offended anybody. I'll stop there. Thank you.
Thank you, George. It's just what we were hoping for, thought-provoking. So questions, you can